Hi, welcome back to Calculus. Today, section 3.11, linearizations and differentials. So we're going to basically use calculus here to cheat just a smidge. And it's not really cheating, but kind of seems like it. All right, so the idea here is that close to a point, a tangent line is a really good approximation of a curve. So you can see I sketched a parabola, we have a point, and I have a tangent line. The closer we are to the point, the closer my tangent line is to this parabola. And so that's really the idea we're going to be working with here. Lines are easy. We know a lot of stuff about lines. I mean, those are like the first graph that you ever learn when you take algebra. So we know a ton about lines. We don't always know a lot about a curve. Now, we probably know plenty about parabolas, but pretend it's something much uglier. So what we're going to do is we're going to cheat the system just a little bit, and we're going to use the line to approximate values on a curve. So I have to clear this board, we'll get another board, and we'll see how this works. Okay, another short board where I just talk about some stuff. If f is a differentiable function at x equal a, so you have to be able to take the derivative at this point, then the approximating function L of x, which is equal to f of a plus f prime of a times x minus a, is the linearization of f at x is equal to a. And this is just an equation for our tangent line. That's really all that this is. A is considered to be the center of the linearization. So we're just going to take advantage of this. So notice what we have. We're going to have a function f. We can certainly plug a number into it and get an answer out. We can take its derivative and plug a number in. And then yeah, let's see what happens and see how we're going to make this useful. All right, so now we want to find a linearization, and we're going to put it to some use. So find the linearization of f of x equal to the square root of 4 plus x at x equals 0. So I first thought, okay, well, I need to take this derivative. It's going to be a little bit easier if I write the square root as a 1/2 power. I also know I'm going to need f of 0 because remember that's part of our linearization, f of a. In this case, a is 0. So if I plug in 0, I get 2. So for the derivative, I drop my exponent down front, times the 4 plus x to the negative 1/2 power, right? Subtract 1 off that exponent. Be careful, this one it doesn't end up mattering, but we do have an inside piece, so we need to take its derivative using the chain rule. The derivative on the inside, though, is just 1, so that works out pretty nice. So I rewrote that, I brought it down to the bottom and turned it back into a square root. So I get 1 over 2 times the square root of 4 plus x. That's my derivative of f. Then I plug 0 into that because, again, if you remember our linearization, we need f prime of a as well. So if I plug in 0, I get 1 over 2 times the square root of 4. Square root of 4 is just 2, so 1 over 2 times 2 gives me a derivative of 1/4. So the linearization function, or the approximating function here is 2, there's f of 0, plus f prime of 0, 1/4, times x minus a, but a here is 0, so we just end up with 2 plus 1/4 x. So then I want to use my linearization function to approximate f of 0.1. Well, the linearization at 0.1 is 2 plus 1/4 times 0.1, which works out to be 2.025. The actual value would have been 2.002498, which gives us an error by subtracting those two of about 0.0225. So you can see this isn't too far off at this value that's very close to 0. Again, if we got farther away, the linearization isn't going to do as good of a job. So 0.1, that's pretty darn close to 0. Far away, they wouldn't do as nice of a job. All right, next up, differentials. All right, so next up, differentials. So we want to let y equal f of x. I can talk. Let y equal to f of x be a differentiable function. The differential dx is considered to be an independent variable, so we're going to plug numbers in for that. And dy, the differential y, is equal to f prime of x times dx. So notice I have an equation y equals x to the 6th plus 8x here. Basically what's going to happen is we're going to take a derivative, just like we normally would. The difference is we're going to treat x like we have to do a chain rule on it. Even though that's not very normal at all, That's what we're going to do. We're going to treat x like something that we have to do implicit differentiation with. So let's find dy for y equal x to the 6 plus 8x. So we just need f prime of x and then to multiply by dx. Okay, not a big deal. This is just a nice little polynomial. So the 6 comes down front. We get 6x to the 5th. For the 8x, we just are left with the 8. The x disappears. So there's f prime of x dx, just like what we had over here. For part B, I want to find dy when x is equal to 1 and dx is 0.3. So all I did is I just plugged in numbers. I put in 1 for x and 0.3 for dx, and I worked it out and we got 4.2. Now, what is this really saying? Well, this is saying that for this particular function on y, that when x is 1, if you make this little change of 0.3, you get that, in this case, quite a bit larger change in y. And so it's really kind of a descriptor of how x and y are changing together when x is 1. Okay, so that's really kind of what we're working with here. That's sort of what a differential is. All right, so now I need another board so we can keep going. So here I just have another quick little example. Find the differential of x over x plus 1. So we're really just going to treat x again like we have to do a chain rule on it every time. We're really doing implicit differentiation. So this is a quotient rule, so I have the bottom times the derivative of the top, which is 1. But because it's an x, when you take its derivative, you need a dx. Minus the top times the derivative of the bottom, which is also 1. But again, with that dx, and all over the bottom squared. So I cleaned it up a little bit. Notice I am working with dx here just like I would any normal variable. So I distribute it. I get x dx plus dx, and then minus x dx. The first and last pieces there cancel out, so we just are left with dx over x plus 1 squared. And yeah, there we go. All right, let's keep going. A little bit more, and then we'll actually be done. Okay, so I want to start working on this problem. There is going to be a part B. We'll do it here in just a second after I have some more space. Sorry. All right, so the radius r of a circle increases from 10 meters to 10.1 meters. Part A, use dA, the differential of A, to estimate the circle's area when the radius is 10.1 meters. All right, so here's all the fun work. First, I wrote the area as a function of r. So A of r is equal to pi r squared. That means that the differential of A is equal to A prime of A. Again, A is going to be 10 times dr. And we know that dr here is 0.1 because that's the change from A, right? A is 10. We're looking at 10.1, so we're looking at a change of 0.1. So I take the derivative, which is 2 pi r. We're going to drop that 2 down. But then we have that dr, and then I just plug stuff in. R is 10, dr is 0.1. 10 times 0.1 is just 1, so we're left with 2 pi meters squared. That is not the area at of the circle at 10.1. That is the change in the area from 10 to 10.1 according to the differential. So by this process, the area is going to be the area for a circle of radius 10 plus that differential. So if you plug 10 into the original area formula, you get pi times 10 squared plus the differential, which is 2 pi. 10 squared is 100, so we have 100 pi plus 2 pi. We get an answer here of 102 pi meters squared. This is an estimate because the differential, of course, is not exact. It's going to be pretty close here, but yeah, it is an estimate. But it's kind of a nice one, right? We don't have to. This would have been a lot better. Okay, let's face it. You can plug 10.1 into your calculator and get the area really easy. But once upon a time, before calculators, this would have been a much easier process to go through than trying to work with 10.1. All right, let's see part B in just a second. Okay, so for part B, you can see I left this information still here. Part B, I just want to compare what we got, 102 pi meters squared, to the actual area. So now we're going to use our calculators. The area, if you have a radius of 10.1, is just pi times 10.1 squared, which works out to be 102.01 pi meters squared. So that's a lovely number, And notice that's really, really close to what we got. We got 102 pi, that's 102.01 pi. So the difference, I just subtract those two things, the difference is 0.01 pi. That's not much. If you plug in pi there, you get a difference of about 0.0314 meters squared. Again, not a whole lot. All right, one more example and we'll be all set. Okay, last example. We want to estimate using differentials the third root of 26.95. Lovely number. What it has going for it is it's really close to 27, and we do know the cubed root of 27, which is 3. So that's going to really suggest some things here. I want to use my function here as y is equal to x to the 1/3 power. Remember, 1/3 power, third root are the same thing. So I'm going to use this as a function to try and estimate this value. Once I have a function, I can take its differential. The differential of y will be, drop that 1/3 down, so 1/3 times x to the negative 2/3 power dx. I chose to write that as a fraction, 1/3 times x to the positive 2/3 power, and then times dx. And so now, we're just going to work with some things that we know. We know we're really close to 27. So I'm going to let x be 27, and then the change in x is a negative 0.05. Right, that gets us from 27 to this value over here. I plug those in, and if you work that out, you get that the differential of y is negative 0.00185. But remember, this is the amount that y changes if we change x by this little tiny amount, which is what we need to get the cube root that we want. So I say, okay, the cube root of 27 is 3. That means that the cube root of 26.95 is about 3. And since it's negative, we'll have a minus 0.00185. It works out to be about 2.998. You could drag out a few more decimal places if you really want, but probably you don't need to. And so there we go. There's our third root of 26.95. Again, it's an estimate. It's not exact, but that's okay. So there you go. That's linearizations and differentials. Have a wonderful day.